Hello, everyone. We are case study number 4, and we're going to be discussing clustering, specifically a couple methods on determining the optimal number of clusters or the K value.
So why do we cluster? Why is this an important algorithm for us? Clustering groups data on a similarity basis. So this can be very useful for a host of different applications, such as biology, marketing, sports analytics, police work, etc. Almost any realm of data science, this can be a very helpful tool for numerical data. So for example, if we pretend that you're a basketball coach, you can collect the number of jump shots, three-pointers, layups, rebounds, assists, steals, blocks, and any other pertinent info that a player makes during a series of games. And you could potentially use that numerical data and cluster it, and you would be able to improve their training regimen by seeing which skills they're really good at and which they're not, and you can give them a personalized training plan. However, with clustering, starting is really the hardest part. And the very beginning step is choosing K, which is the number of clusters that you're going to be using in your algorithm. So as can be seen on the plot on the left, sometimes choosing K can be really easily, and you can do that with data visualization. So in that plot, it's very obvious that there are 5 clusters. However, what if your data is really highly dimensional? What if the clusters are really unclear or you don't have a way to visualize it? How are you going to choose K in that kind of scenario? So there are 3 methods that we use for this, and they are the elbow, the silhouette, and the gap statistics methods, the first of which is going to be elbow.
So first we have the elbow method. This is just a general overview of what the elbow method. Simply put, you're going to choose a group of values of K to test, and you're going to do some trial and error by plotting the explained variation versus the cluster size, and then choose the optimal number of clusters based on where the plot elbow is, which is something I'm going to explain further in the next slide. So first, just some background to explain the logic of where the elbow method originates from. As we all know, a perfect clustering solution can be put simply by minimizing the within cluster sum of squares. And what this fancy term basically means is we're trying to find the minimal distance between all the points within a cluster. However, when you really start to dig deep, you realize that this is not actually the best way to describe our overall goal. So to do this, let's talk about some extreme case issues. So for example, let's let n equal the number of observations and k equal the number of clusters, which is the standard variable. So when we make n equal to k, in other words, there is the same number of clusters as there are observations or vectors or rows within your data, then the WCSS, or within cluster sum of squares, becomes 0, which is technically minimized. However, if we look at 2 cases of this, for example, if we have here on the left, we have a plot of 5 points, and sure enough, we have made n equal to k and put each one in its own cluster. So when we calculate the distance between each data point and the others in its cluster, the value is 0 because there's only 1 in each cluster. Similarly, at the other extreme is we have a lot of data points or observations, and still there's only 1 in each cluster, so n equals to k, and it's technically minimized. However, as you can see, there's no value or insight added. We just have the same thing we started with, which is individual clusters with each data point. And thus, a better way to say it is that the true goal is to minimize the WCSS while also trying to minimize the number of clusters. And that is the logic behind the elbow method. So to carry out the elbow method, we take the WCSS, so the distance between each point within a cluster, and we plot it against the K value, or the number of clusters. So in this example, you can see the values for K that we're testing are 2 through 8. It's quite a few numbers. And when we plot them against the WCSS, we get this curve-like feature. And if you look at the beginning of this feature, 2 to 3 clusters, 3 to 4 clusters, we see a rapid decline. However, we reach a point after this, noted in purple, where there's not much of a decline. We see the slope is a lot more subtle, 4 to 5 versus 5 to 6 clusters. And then you can isolate a point where we see this transition. And this is something we call the elbow. And once you found that elbow point, then you trace down to the x-axis And in this case, we see 4, and that becomes the optimal value of K, where we have minimal clusters while still seeing a big improvement in minimizing the distance between the points in each cluster.
So let's look at a sample workflow of what the elbow method would look like if you're using it in real life or on a data set of your own. So for this example, we're going to be using the iris data, which is a set of data points that has the sepal length, sepal width, and petal length and width for 150 different flowers, along with their variety. So the first step in this process is to import that data, import the cluster and facto extra library, and then we're going to prep that data for a clustering analysis, which in this case would include removing that variety column, since clustering only works with numeric data. So we would get rid of that. After this, you could take that data and you could input it into a k-means, into an elbow method. And we would do this through the NB-clust library. And you could choose any k-max. We would recommend maybe doing a little bit of exploratory analysis, testing what values look good. And for our data, it seems like a good maximum K would be 5 or 6. So in this example, we pick 6, and then we're going to use the within sum of squares method, just as Natalia mentioned earlier. So when we run that code on the iris data set, you can see this plot that appears on the right-hand side, and that shows that the number of clusters is likely K equals 2, since there's a pretty extreme elbow right there at the K equals 2 point. So you would be able to take that K equals 2, and you can input it into your clustering code for wherever you're going to do your k-means clustering. The resulting clusters are shown here with the iris data. So you can see from this two-dimensional viewpoint of the iris data that there are 2 pretty obvious clusters, just as the elbow method predicted. And then there is also an example of what it would look like if we just chose a random K, say K equals 5. And you can see that the clustering is just not as good, since there are 2 pretty obvious clusters here. And that concludes the elbow method.
Hi guys. Now I'm going to explain select method, which is one of the cluster validation techniques. Before explaining this, let's repeat what Vicky and Natalia said. We have been using elbow method as a method to find the number of optimal clusters for our data. For example, we have used iris data set to find the optimal number of clusters. We got K equals to 2 by using elbow method. But we can't trust elbow method, right? We have to validate that the K value. So we are going to use different clustering validation techniques to find the number of clusters. One of the method is silhouette method. This silhouette method is a validation technique which uses silhouette score as a metric. This silhouette score is a measure of how similar a data point is to its own cluster, that is the amount of cohesion, and how different is our data point to the data points in other clusters, that is the amount of separation. This silhouette score ranges from -1 to 1, where a high score indicates that our data point is well matched to its to our own cluster and well separated from the neighboring clusters. Let's compute the silhouette score. There are 3 steps involved. There are 3 main steps involved in computing the silhouette score. First, we're going to compute A of I. This A of I is the average distance of each data point to all the data points in our own cluster. That is in a single cluster. Here we can see that, let's take this green cluster. Let's take this is our data point. We are calculating distance to all the points using a distance metric. Let's say Euclidean distance. We can use magnetic distance as well. Let's say Euclidean distance. After finding distances to all the points, we are going to average by the number of points. Here, see, we are doing -1 because we are not calculating distance to itself. That is, this data point to this data point. By this, by computing A of I, we are going to get the amount of cohesion for our data point to its own cluster. The second step is to compute B of I. This B of I is the average distance from our data point to all the data points in the nearest neighboring cluster. See, how am I saying the nearest neighboring cluster is? We are calculating the average distances to all the clusters and taking the minimum one. By calculating this B of I, we are going to get the amount of separation from our data point to all the clusters. See, we are averaging this with the amount of with the number of points. The third step is to compute the select score. We're going to compute the select score using this formula. The B of my in the numerator we have B of B of I minus the A of I, the amount of separation minus the amount of cohesion. By this formula, we can say that B of I should be always greater than A of I to get a positive select score. If we get select score less than 0, by that we can say that the clusters are not assigned in a correct way and the data points are overlapped between the clusters. That is, the clusters are overlapped. If you get a high cluster select score, that is 1. By that we can say that the clusters are well separated from each other and the data points are well separated from the neighboring clusters. By this select score, we can say that it is a better technique compared to elbow method, because in elbow method, the main aim is to reduce the amount of variance. Here, there we are taking the point where there is a drastic change in the reduction variance. But here we are also considering the amount of separation for our data points to the neighboring clusters as well. So I think elbow method should be done, but we have to validate the results are from the results from the elbow method by using other validation techniques like silhouette method, gap method, etc.
And coming to the coding part of the silhouette method, we are going to use these two particular libraries. One is silhouette samples and silhouette score, and where silhouette scores is used to find the average scores of the average silhouette scores, and to find the individual silhouette scores, we are going to use this particular library from sklearn, and we are going to import these libraries for the plotting of the graphs, and we are going to import the iris dataset. And based on the elbow method, we have found that k equal to 2 to be an optimal value, and that we are going to validate using this particular silhouette method, whether k equal to 2 is a better choice or not. So initially we are going to initialize the clusters from 2 to 6, like we just took like random values from 2 to 6, and then we are going to iterate inside this particular for loop. And initially we have initiated a figure object with the two subplots ax1 and ax2, where ax1 is a silhouette plot and ax2 is the clustering plot. So and then we are setting up the x and the y limits of the plots, and then we are going to use the k-means, where we are going to send the different values values of the k from ranging from 2 and to the 6, and we are going to iterate it, and then we are going to send the and then we are going to set the random state equal to 10, and then we are going to get the clustering labels when we use the fit method. So after that, we are going to calculate the silhouette average, for which we are going to use the x values, all the values of the x and the respective cluster labels. And within this particular code, line of code, we are going to calculate the AI and the BI and the SI, like this particular formula that is going to compute in this particular line piece of code. And then we are going to print all the values of the averages of different values of the k, and then we are going to get the averages for different particular k values. And later we are going to set the lower limit of the y, and we are going to set the lower limit and upper limit and the size of the clusters based on the different value of the k. And we are going to use the area fill for different silhouette, and parallel to different value of the k, we are going to also plot the clustering graphs. So this is all the visualization part, like the color coding and that stuff. And we can see them and coming to the execution part, here we can see the different values of the silhouette score for different values of the k, and based on these values we can't really say anything about which value is better. So we have to look at the graph, and when the k value is 2, we can see that there seems to be a negative values in this particular range from minus 0.1 to 0. That means that AI is greater than BI, and that means that clusters are assigned in a wrong way. So we can't really go for that. So when the k is 3, we can see that there seems to be we don't really see any kind of negative values. And we can also see in the graph that they are actually having a different clusters. And so we can actually consider this particular thing. Let's see when the k value is 4. So here we can see that there are some negative values. And when the k is 5, we can see negative values. And when the k value is 6, even then we can see the negative values in this particular region. So that makes our conclusion easy that k value 3 seems to be a better value of the k. So for the k means clustering.
Gap statistics method is a data-driven approach used to determine the optimal number of clusters for a given dataset in unsupervised machine learning. The goal is to identify the most appropriate number of clusters that accurately represents the underlying structure of the data. Examples of data that can be clustered using this method include customer segmentation data, medical diagnosis data, and natural language preprocessing data. And this method involves several steps. First will be understanding and preprocessing the data, then choosing the clustering algorithm, generating the reference data sets, computing the gap statistics, and then choosing the optimal number of clusters. Next slide. So gap statistics is computed as the difference between the expected value of the within cluster variation and the observed within cluster variation. Formula for computing gap statistics is gap of k equals to E of log wk minus log of wk, where E of log wk is the expected log of the within cluster variation for the reference data set, and log of wk is the observed log of the within cluster variation for the original data set. To compute the expected value of the within cluster variation, we first need to generate a reference data set from a null reference distribution. This null distribution can be Gaussian or uniform depending on the nature of the data. We then need to compute the within cluster variation for each of these reference data sets and take the average of the log of these within cluster variations to get E of log wk. To compute the observed within cluster variation, we first need to cluster the original data set for different values of k and then compute the within cluster variation for each value of k. And then we need to choose the optimal number of clusters as the value of k that maximizes the gap statistics while also assuming that the gap of k is significantly larger than the gap of k plus 1. Yeah, over to Sai.
Hi guys, as Puja covered the theoretical part, now I will explain the coding part of the gap statistics method. Here we use the Irish dataset. We downloaded it from Kaggle and we cleaned it up. And we use this dataset to explain the gap statistic method and how many optimal clusters can be created for this dataset. Now I will explain the coding part for it. 1 minute. Yeah, this is the R code for the gap statistic method. These are the required libraries we need to load before running the data. So here I read the CSV file from my local machine Irish dataset. And as we all know, the gap statistic, these clustering methods are unsupervised modeling. So I removed the label from the data. So it don't have the label. And I also normalized the data with using the scale function. So we get the normalized data. And now I will go to the NB cluster library to generate the number of optimal k values, and I use the method as a gap statistic method. And this fun is used for the which algorithm to choose. Here I choose the k means as the algorithm, and this k max value can be anything like based on your convenience. Here I kept it as 5. So this one is the plot when you run this line. So you can see the highest peak at number 3. So gap statistic method is suggesting k value has to be 3 for the best clustering image. So I also did with the hierarchical clustering also with this method. So it also shown me the same value as the k value as 3. So I generated the number of clusters using the k as 3. So this is the image I got when I put K as 3. So we have 3 clusters with 3 centroids. So these 3 are the centroids. So, but the elbow method suggested the K should be 2. But we all know that in general, we all know that the gap statistic method is the most reliable and robust method for choosing the K value than elbow method. So by this way, we can calculate the K value using the gap statistic method. Now, Roja will take over and say the importance of the clustering. Thank you.
Importance of clustering evaluation methods. So one of the primary goals of clustering is to group similar data points together into meaningful clusters. However, determining the optimal number of clusters is often a subjective and challenging task. Clustering evaluation techniques such as silhouette, elbow, and gap methods help to determine the optimal number of clusters for a given dataset objectively. The quality of clustering results can affect the interpretation and application of the clustering results. Clustering evaluation techniques help to ensure that the clustering results are meaningful and interpretable, enabling researchers to make accurate conclusions and recommendations based on the clustering results. Clustering evaluation techniques can also be used to identify outliers or anomalies that do not fit well into any of the clusters, which can be useful in outlier detection and anomaly detection tasks. Next slide, please. If no thought is put into number of clusters used in clustering models, several problems can arise like overfitting or underfitting. If the number of clusters is too high or too low, the clustering algorithm may overfit or underfit the data. Overfitting occurs when the model is too complex and fits the noise in the data rather than the underlying patterns, while underfitting occurs when the model is too simple and fails to capture the underlying patterns in the data. If the number of clusters is not appropriate for the data, the clustering algorithm may produce inaccurate or meaningless results. For example, if the data can be divided into 2 clusters, but the algorithm is set to identify 4 clusters, it may split the data into 4 groups that do not represent meaningful patterns in the data. As the number of clusters increase, the computation time and resources required to perform clustering also increases. If the number of clusters is not appropriate for the data, the algorithm may take longer to converge or require more memory, leading to slow performance and increased computational costs. Next slide, please. So why does different algorithm produce different results? Clustering algorithms may produce different results for the same dataset due to various factors, including sensitivity to initial conditions, different distance metrics, and ambiguity in the data. Clustering models are based on measuring the distance between data points, and the choice of distance metric can affect the clustering results. For example, the choice of Euclidean distance versus Manhattan distance can produce different clustering results. In some cases, the data may have ambiguous or overlapping clusters, making it difficult for clustering algorithms to identify the correct clusters. In such cases, different clustering algorithms or parameter settings may produce different but equally valid clustering results. It is essential to consider these factors and evaluate the clustering results carefully to ensure that the clustering method used is appropriate for the data and research question at hand. So to conclude, each of these methods has its own strengths and weaknesses, and it is often recommended to use multiple methods to obtain a more robust estimate of the optimal number of clusters. It is also important to consider that these clustering evaluation methods cannot be overstated, as they provide valuable insights into the structure of the data and enable the development of more accurate and effective clustering models. Thank you.